Hello, I am Davis Catherman, and this is Team Christopher Newport University Imprint. I am a junior at CNU, and this is my third year on the team. As the mission commander, I oversee the entire process of development and ensure members are trained for competition. I will be the lead coordinator of the flight line.
I'm Bashir Davis. I'm a junior at CNU, and this is my third year on the team. As the flight team lead, it is my responsibility to safely test a competition aircraft and determine its airworthiness. I will also be a safety pilot this year at the competition.
I'm Eric McLaughlin. I'm a junior at CNU. I serve as the ground stations operator. So I'm in charge of planning missions and testing them to make sure they function properly when the plane goes to fly.
Hi, I'm Cameron Calpin, a junior at CNU, and as ground station and payload manager, it is my responsibility to ensure that the flight mission includes optimal readings from the plane to the ground station and managing imported images taken from the plane.
I'm Yamin Ayub. I'm a junior at CNU, and this is my first year on the team. I'm a member of the software team, and on the flight line, I'm in charge of image processing.
Competition aircraft is a ready-made RC Anaconda. It is a twin-boom design with an inverted VTOL and fixed landing gear. The aircraft's wings are covered in high-contrast tape to distinguish the orientation of the aircraft in flight. It is powered by two 4-cell LiPo batteries that allow flights easily up to half an hour. This all ensures safe flight operations. The gimbal houses the camera in the belly of the fuselage. It was custom designed and printed. It uses two servos to counteract the longitudinal and lateral axes of the aircraft.
We have several electrical systems. We use a 3DR Pixhawk as the autopilot due to its robust operational ability. The camera system includes an onboard Raspberry Pi that receives images from the camera for the image recognition tasks. A 5 GHz bullet data link permits communication between the Pi and the payload computers, allowing for the completion of the actionable intelligence task. The RFD900 telemetry link allows for a greater range compared to the standard 3DR radios. This 900 MHz link provides more consistent communication to the aircraft from the ground station computer.
The ground control station consists of several pieces of software. The first is the use of MAV proxy. MAV proxy routes the telemetry data to all devices that require it on the ground station. Mission Planner receives data from MAV proxy. It is used for planning missions and monitoring the flight of the UAS. This software is run on the main mission control computer. The next main piece of software used is the custom interoperability code. As this software is custom designed, this software will be discussed in more detail later. The final software package used is our custom target recognition interface, known as Image Manipulation Genie. This will be used to post-process the images in an efficient manner with partial assist features.
For our planned tasks this year, we will be attempting the waypoint tasks, the target recognition tasks, including the search area grid, the emergent target, and the off-axis target. We will also be attempting the actionable intelligence and the interoperability task, including submission over the interoperability system. What we will not be attempting includes the air delivery and the obstacle avoidance tasks. For all of our tasks, we expect a high performance through our intense development, as you will see further outlined throughout this video.
The interoperability system is split up into different sections that each deal with an approach to solving each individual problem with regards to the task parameters and the overall tools provided to us at the competition. Our system starts with a back-end interface. In contrast to previous years, where an app's components were built together with no overlapping functionality, this year we split up everything into a more modular approach to solving the problem. The system involves the ability to receive telemetry data from the plane. This was accomplished with the MAVLink package that is native to the Python Development Package Manager. This was integrated with functionality from the competition server to more adequately utilize the data and post-telemetry data. Our system used the API provided in the competition server's client interface. This allowed us to integrate our system with the competition server very easily.
For developmental testing, we followed a procedure that consisted of starting with a few devices and ensuring they are all communicating properly. First off, we started with the camera and the Pi. Now, once those were functioning properly, we then added the autopilot software to the camera and the Raspberry Pi. Last but not least, we added the data link to the autopilot, the Pi, and the camera all together, and made sure those all were functioning and communicating properly. So this procedure is beneficial in locating flaws because we can confirm a device is not communicating properly with the other devices and easily target the issue the device is having.
A big part of its endeavor was testing. We constantly tested our software with its ability to handle data, its stability, and its overall functionality with external components, such as the competition server. Our testing medium came through using a common testing tool known as software in the loop, or SITL. This allowed us to simulate a plane flying overhead, which would send telemetry data to our interoperability system. When developing the display and front end, the simulation software gave us a comparison to make sure that our display was as close as it could be to that the simulation software gave us. This was primarily simulation testing and was conducted throughout the year with the numerous testing runs and loops. It provided a foundation for our software to enter real flight testing. In this stage of testing, we would actually go out to a flight field and test an actual flight with the program. It allowed us to confirm that the system was functional, as well as give us some practice runs on how to use the software that we were using. This has not only prepared the software, but prepared those on the flight line and the ground control system. It enhanced their operational capabilities of the system itself, allowing them to better identify errors, where they were occurring, and how to fix them when they came up. As we all know, there's nothing routine about these flights.
For the mission waypoint task, we used an accuracy value of 10 feet. Numerous testing has shown that we are able to maintain this value of 10 feet. The only notable exception occurred when we experienced crosswinds, and even then we were able to maintain an accuracy value of 15 to 20 feet. We visually ensure that our UAV is maintaining this accuracy through the ground station mapping system. We have the capability to execute a waypoint again in mission as necessary via the ground station computing system.
Through testing, we determined to have lower image blur and more distributed ground coverage using our custom 2-axis 3D printed gimbal over a traditional rigid mount so that it may correct for the roll and pitch of the plane using the Canon G15 camera. The target may be accurately depicted with a minimum resolution of 50 by 50 pixels. For localization, with each camera trigger, the Pi records the orientation and GPS location based on telemetry from the PixHawk of where each picture was taken. Using various predefined calculations, our assisted image processing program accurately determines the coordinates of the target of within 15 feet.
We conducted several full mission tests. For these tests, we performed autonomous flights, including takeoffs and landings. We also completed the tasks that we will be attempting at competition with the team members fulfilling the roles that they will be performing on the competition flight line. For these trials, we also purposely tested the need for the safety pilot to take immediate control of the aircraft. One of the flaws encountered as we worked towards the full mission test occurred during the autonomous takeoffs. It was noted that the plane would steer off of the runway. After breaking down the problem into components, we were able to determine the cause and reconfigure the parameters on the autopilot. We were able to also ensure that the aircraft auto-corrected for the steering through on-ground testing before continuing with full mission tests. Our expected score calculation is based on the fact that we will not be attempting the air delivery or obstacle avoidance tasks this year. The greatest mission score achievable is therefore a 70%. This will be referenced as our 100% accuracy level. For the waypoint accuracy, we successfully averaged 95% or greater. Then, due to the potential of missing a target, we are able to achieve an average of 90% for the image recognition task. We are able to reliably score 100% on the autonomous flight task. As a result, we expect our final score to be 90 to 95% of our attempted tasks. This is Christopher Newport University Imprint, and we are expected to have a great flight at the competition this year.